Good morning. Welcome back to Physics 4C Lab. This week we have just started the chapter 36 on relativity, special relativity, and we're finding there that this physical constant c, which we talked about in chapter 36, it's really a space-time conversion factor. So it's a lot deeper. There's a lot more depth to it. It's not just the speed of light. Light just happens to travel at that speed because photons are massless. If photons had mass, they wouldn't be traveling at c, they would be traveling at different velocities anyway. We're going to go ahead and call the lab light speed, and we're going to say our objective for the day is to measure the speed of light. And to me, this is one of my favorite labs for sure. We do a lot of really interesting labs, but it's kind of remarkable to me that we can measure the speed of light right here in the physics lab room. We don't need all that much space. There's enough distance here that as light goes back and forth, there's enough of a delay in how much time it takes for light to go back and forth across the room that we can actually do this measurement right here in the lab room. When I first started teaching at Laney and became familiar with some of the lab equipment around here, and I found these notes that were left by a professor who had just retired, and I started looking at these notes for this lab, and it was just astonishing that this could be done, but hey, it's great, it really works. The idea with this is that, and we'll do a walk around in the room in just a minute. I just want to do some board work up front. We've got a laser source back over here, and the laser is pointing at this mirror. So if you look at this closely, there's a mirror inside here. This is a really high-speed rotating mirror. So I've got a voltage supply here. So this mirror rotates at speeds up to 640 rotations per second. Okay, so it's really this high-speed motor with this mirror attached that allows us to do this measurement, and here's how it plays out. The light comes in, the mirror is rotating constantly. Now, the light is going to catch the mirror at one orientation. So the light strikes the mirror, bounces off the mirror, another part you can't see right now. There's a lens and then a series of mirrors. I think this is in your field of view. There is a mirror out here. So we're going to send the light all the way to the back of the room where there's a mirror, and then we're going to bring it to this mirror, and then we're going to send it right back along the path it came from. Now you would think, light's really, really, really fast. By the time the light runs over here, out to this mirror, back in the room, to here again, how much time has really passed? And it turns out it's not that much. Light speed, we've talked about in class, light travels about 30 centimeters in a nanosecond. So we could extend that to the back of the room and back here. It's like 30 meters. And so 30 centimeters, it's like 100 nanoseconds or something, is the amount of delay of the light traveling back and forth. Now, at 100 nanosecond delay, how far could this mirror have rotated? But it's enough. It turns out that the mirror is going to rotate ever so slightly during that time. Remember, it's rotating like 600 times a second. And so by the time it goes back to the location where it came from, the returning light has shifted. As we turn up the motor speed, the returning light shifts more and more. And it turns out that we can get several millimeters of shift. So, and if we get a good ruler set up and we get a good view of the image of the return light, that's enough that we can measure the speed of light. So let me take a look at this on the board. So, and I think it'll make more sense once we do the walk around with the lab setup. So here is the laser. Laser is sending light towards this rotating mirror. It strikes the mirror at some angle of incidence. It reflects at some same angle, and then it travels along the classroom, and then it makes its way back to the mirror. By now, the mirror has rotated, so the return path is shifted by an angle of 2 times phi. Now, since the mirror has rotated by angle phi, that means the returning light has an additional angle of phi in its incidence, and that means that both the incident and reflected light will experience that additional factor. So the return light is going to be shifted by an angular distance of 2 times phi, where phi is equal to the rotational speed of the motor times the delay time. Now, how long could the delay time possibly be? Well, the delay time is however far it took to go all the way out to this distant mirror and return. That, I'm going to call that distance b. That's distance b out, distance b back. That's 2 times b. So 2 times b divided by the speed, by the velocity, which we're going to call c. So this is the delay time. How much delay time are we going to have? And it turns out that the deflection that we see, if this light coming back travels back a distance a to where the laser is located, and it's shifted by an angle of 2 phi, that's going to create an arc distance. And that arc distance is going to be the radius times the angle. Now that's such a small angle that can easily be written a times 2 phi. So putting all of those 3 pieces together, we make a prediction that there will be a shift in the return light, or a deflection. Maybe a shift is a better way to think about this. A shift distance given by multiplying all the factors together. 8 times pi times a times b times the frequency of the motor, and let me write that in. So this is the frequency in hertz of the motor turning around. We went from radians into hertz right here, put in that extra factor of 2 pi, all divided by the speed of light. So that would tell us how much deflection we're going to have, but we're going to flip that around. So instead, we're going to set it up so based on the observed deflection, we can calculate a speed of light. Yes, right here in room A274 at Laney Community College, we're going to get a reasonable measurement of the speed of light within this room. All right, now there's some optics that are going on here, so let's talk about that a bit. I mentioned that there's a mirror, there's a lens and some mirrors. We're going to start from an object. Now the object is the laser itself. Now if we just send light out from a laser, it doesn't remain a tightly collimated beam. What happens is even laser light over a distance is going to spread out. Now when it leaves the laser, it's this little tiny millimeter size image or object. Object is what we're going to refer to it as. When it returns, that's going to have spread out a lot. That is not going to allow us to make a measurement. We need to get it to come back to that really tiny sub-millimeter diameter. And the way we do that is to get a nice sharp image of the return light, we put a lens halfway through. So the light spreads out for half the distance, and then the converging lens brings it right back together to a point. So that's going to give us a sharp point out here at the distant mirror. So let's say here's the object, which is the light coming out of the laser. In order to have this light be brought back together, we want an object distance of 2 focal lengths and an image distance of 2 focal lengths. Now, I apologize, I use little f for 2 items here. I use little f for the frequency of the rotating mirror, and I've also used it for focal length, but I think they're distinct, so don't get those 2 mixed up. Anyway, the focal length, I'll write that here. focal length of the mirror that we're using. It's a precision mirror, lens, I'm sorry, it's a lens, 5.00 meters. And so that says we need 10 meters on each side. We need 10 meters between the location of the laser and the location of the most distant mirror. So that is what we're looking at. Okay. Now, that's going to be 10 meters on one side, 10 meters on another. There's one more issue that comes up with the optics of all this, and that is when we have light from the laser coming towards this rotating mirror, the rotating mirror is going to take that light and spread it around the whole room. Most of the light's never going to make its way back. The only light from the laser that actually will be able to travel back and forth all the distance is going to be the light that happens to pass through our lens. So I've got this converging lens here. I've got a picture of it down here too. So here is the converging lens. As this light sweeps across the lens, only that small portion, it's going to be less than 1% of the light actually returns. It's a very dim signal that comes back. And so only those students with exceptional eyesight are able to, well, actually most everybody's able to see it, but it's really faint. And so as it sweeps across, what we need in order for the light to continue across the room and back, the light coming out needs to be parallel. If the light is not traveling parallel to the alignment that we've set up, that light will be lost. And so we need to have a mirror rotating right at the focal point of that lens. And that means that we need the mirror, the rotating mirror, needs to go right here. All right, so what that gives us is the rotating mirror needs to be right at the 5-meter mark. That's going to take this 10 meters and divide it up into 5 and 5. Now, on the diagram, we identified two different distances. Distance A is from the laser to the rotating mirror. So distance A, it turns out, needs to be 5 meters. And distance B is from the rotating mirror through the lens all the way to the distant mirror and, well, to the distant mirror. So B is going to represent this distance. A is the distance right here. Ooh, at the risk of really mucking this up. So that is distance A. That is distance B. There, the color worked. So A is going to be 5 meters. B is actually going to be 15. So that's going to be 15 meters, and those are going to go into our formula. So 8 pi times 5 meters times 15 meters times whatever speed we're spinning the motor divided by the shift that the light, the distance that the light shifts. Now, we have to be able to know what the frequency of the motor is, and that is going to be done using a calibration that we put into place. So if you take a look, and we'll get a close look at this when we walk around too, I have a variable voltage supply. Now, how do I know how fast the motor is spinning compared, based on what the voltage is going to be from the voltage supply? And it turns out that I was able to carry out a calibration. So I'll put these are in the notes on Canvas for this. So what happens is this, we have a strobe light, And if I take the strobe light, I'm not going to demonstrate it right here. I think we're going to have issues. I don't think the strobing will work because of the video camera that I'm using is at 60 flashes a second. We'll probably get conflicting strobe effects. But what I did, or what I've done several times over the years, is I've taken the strobe light and little by little, I turn up the speed of the mirror. And when the strobe light frequency matches the mirror frequency, what it does is it makes the mirror look like it's standing still. So I can start at no rotational speed at all. And then what I can do with the strobe light is one at a time, I can go up through different frequencies. If the frequency of this matches the strobe light, it looks like it's standing still. If the frequency here is 2 times the strobe light frequency, that also looks like it's standing still. And 3 and 4. Any integer multiple of the strobe light frequency creates the effect where it looks like that rotating mirror is just standing still. So it takes, it takes an afternoon to do this. So when I've carried out the strobe light calculations, we kind of go back and forth. But what I've come up with is this. I've come up with this calibration where I've identified at different voltages what is the motor frequency. Okay. Now you might say, well, how do we trust the strobe light? At least that's what I would say, and that's what I did say. Well, can we really trust the strobe light? Turns out we can't. When I went through and tried to calibrate the strobe light, based on what the strobe light was telling me, it was off by 15% or more. So that's a serious problem for doing this lab. So what I ended up doing was this. I ended up ignoring the scale on the strobe light itself, and instead, I ended up using tuning forks. So I brought out, let's see, a set of tuning forks. I guess that sounds right. So I brought out a set of tuning forks, and when I put the tuning forks in front of the strobe light, I was able to move slowly through the variable frequency of the strobe light, and I did a calibration on the strobe light. So what I found was that for the particular frequencies that I have for these tuning forks, oh, let me try this. Okay, that's a C major chord. It's a, or maybe it's not. It's a G and a C and an E. No, I really am. Oh no, it is a C major chord. Okay, got it. So it's a C, an E, a G, and a C. So anyway, I looked at the possible frequencies. These are pretty simple devices. I'm guessing that these will not vary. I guess I should check it with my phone. I do have a frequency check on my phone. I'll have to do that and see if it's reliable. So I did a calibration based on these tuning forks of the strobe light, and then applied that to the motor. So at that point, I was feeling pretty good. Everything seemed to be pretty consistent. I cross-checked all the frequencies because these frequencies are in a ratio of 4 to 5 to 6 to 8. You guys may have seen that in Physics 4A, looking at harmonics. So these are all harmonics of each other. And so there were certain frequencies that I was able to confirm using the strobe light, and then use that confirmed frequency to calibrate the motor. Everything seemed to hang together pretty well. Of course, there's a little limitations to what we've done here. Anyway, what that leads us to then is we have to set everything out. So usually when we do this lab here, there's only one setup. The whole class participates. And we get out a bunch of meter sticks and some tape measures, and we measure very carefully all the distances. Now, we would like to maintain, you know, ideally it would be great to be able to measure this to within 1% accuracy. That typically doesn't happen because some of these measurements have more uncertainty. In particular, the frequency, the calibrations on the frequency of the motor, the mirror, and then the distance. The distance of shift is only, it's only like a couple of millimeters. So that's all the distance that we have to work from. So here is a data table. So typically the way this works is, you know, we spend an hour or more getting everything lined up very carefully, and I'll do that and show some pictures of that. And then we go through and just do a series of different measurements using different frequencies and very, very carefully measuring distances. And then use those to determine what the value of C is. So that's what I'm going to do now. I've got most everything is set up. I just have a couple of last alignment checks to go through, and then I'll show you a picture of what things look like around the lab room. All right, here it is. Here's the whole setup. So here's the laser, and we have a beam coming out of the laser. I'm going to do this with the lights on right now, and then I'm going to turn the lights off and we'll see everything. The laser actually heads into a plate of glass angled at 45 degrees, and the idea here is, well, let me show you. When the light comes off, some of it reflects off onto that brick. You can see reflections off the front surface and off the back. So there's actually a couple of signals there. Now the light continues, most of the light continues on to that rotating mirror at the front of the room. So here's our rotating mirror at the front of the room with the voltage controls. Here are the calibration curves, the calibration tables that we'll be using. So that thing's going to be spinning. And then what happens is the light gets sent back to the middle of the room. Now in the middle of the room is that 5-meter focal length lens. And then we want to, if you remember, beyond that lens, we need 10 additional meters. Now it turns out we don't have 10 meters, but what we can do is we can add an extra mirror in. So there's a mirror here that sends the light to a distant mirror right up there. And I think if we come in close on that, you can see that laser right in the middle. So that total distance from the lens through the intermediate mirror to the front mirror at the front is 10 full meters. And here is, just so you guys know, here is my stuff for the day in here while I'm doing these labs. And look, I have my mask and I have my hand sanitizer, which turns out to be 100% isopropyl alcohol. So it's really handy to have the supplies here. We use that actually in Physics 4A when we're doing density measurements. But I have my alcohol and my hand wipes and my mask. Anyway, getting back to the lab here. So that's what the whole setup looks like. So let me turn the lights out and give you a view with the lights out, see how this... When we run this lab, the room is completely darkened. I found out that with the room completely darkened, it just wasn't much showing up. So let me show you what it looks like so you can better see. Remember we talked about the light going all the way back and forth through the room and returning through that rotating mirror at the front. And then what that did was it sent the light right back along the same path. Now if you guys remember that 45-degree angle plate of glass on the way back, that leaves me with 2 signals on the screen. So we put a ruler up onto this and keep track of how far those 2 points shift. As the motor speed increases, those 2 signals are going to shift. Now I don't know, I guess it depends on which way the motor is spinning. They could shift to the left or to the right, but with a ruler up there, we are able to keep track of small amounts. I'm going to shift. I am going to turn the motor on just so you guys can get an idea of what this looks like. So here I am. I'm turning the motor on to a high speed. Now you can see what's happening. The light's just spreading around the entire room. And it gets really loud. And if I go back to look at those dots, they've gotten really, really dim. In fact, I have to say I can't see them right now. To see those dots, I'm going to have to turn the lights completely out. Let me set up a ruler and just see if that might show up. So here is what the return signal looks like. I turned the lights all the way off and took a look at that, but it just wasn't showing up. I wasn't able to pick anything up from that, but I will show you what the signals look like. It's much more dim, and then the entire room is just dark. And by measuring just a few millimeters, just a few millimeters. So I've got the brick set up right now so that signal on the left, right up here, is right at 15.0 centimeters. And when we do the run, even at the highest motor speeds, the largest shifts we see are about 3 millimeters. Anyway, I hope this has been interesting. I know it's not as much fun as being here in person and actually running the experiment. But again, this is our setup for measuring the speed of light here in the Laney Community College Physics Lab Room.